All right. We'll let people continue to file in here for just a minute. You are in the right place. This title's a little different than on the schedule. We're going to talk about some of the latest and greatest JVM features, and I'll show you a little bit about how we're making use of them in JRuby. All right, I'm going to get started here as the last few people file in. Going to talk about a few things today. My name is Charles Nutter. I work for Red Hat. Pretty much our primary job is just working on JRuby and exploiting and finding ways to use the JVM better to implement the Ruby language, and then sharing that information with all of you and with other language developers on the JVM. Let's go. I think I've got that slide there. So we're going to run through a few things today. We're going to talk about some of the challenges for building alternative languages on the JVM, especially languages that are like Ruby that have not grown up in the JVM environment. Talk about some of the JVM features that exist today that we are making use of. Features that are upcoming, the experimental features in JDK 19, for example. And then how all languages and JVM users benefit from having languages like Ruby on the JVM. All right. As I said, I'm Charles Nutter. I've been programming for pretty much all my life. Been working on JRuby since 2006, 10 of those years at Red Hat. So we're very thankful for Red Hat sponsoring our project. And I'm a big advocate for alternative languages on the JVM. I believe that the runtime can bring a lot to those languages, and also that those languages help the JVM grow and help us be better developers on the platform. So we're going to talk first a little bit about JRuby. How many people are familiar with JRuby? All right, maybe about half the room. So JRuby is, of course, just the Ruby programming language running on top of the JVM. We can integrate well with Java classes. You can import Java classes and call them as if they're regular Ruby code. We bring parallel threading to the platform, which is a little different from the standard Ruby. And then all of the other benefits of the JVM, of course. We compile Ruby code to bytecode, which then gets JITted to native code, so it's running nice and fast. We get the benefits of the GCs, and all of the continued progress on the JVM we get for free just by running on top of it. It's actually been in development longer than I've been working on the project, since about 2001. But really, in 2006, we hit our stride when we were able to start running full-sized Rails applications. And there are now hundreds, thousands, not sure, but lots of Rails applications out there that use JRuby to scale. Many times that had to make a move from the regular Ruby to get better performance out of their application. We're the only alternative Ruby, the only non-standard Ruby implementation that has ever seen wide deployment. And as I say, there are places all over the world that are running JRuby, banks and governments. And last I heard, there was a fuel refueling terminal at Oslo's airport that actually is a JRuby-based Android app. So lots of fun things and scary things, but we're happy to be continuing to work on it. And we're really pushing the edges of the JVM. I hope that's one of the main things that you get out of this. We have been driving a lot of these features just by need, just by the demand of the Ruby community. So what about Ruby? Ruby is dynamically typed, object-oriented. It's a scripting language, if you don't mind that term. Inspired by several different languages and born about the same time that Java itself came into existence. Of course, the main thing that you hear about with Ruby is Ruby on Rails, used for doing web development. But there are other frameworks for doing smaller microservices. There are GUI libraries for doing desktop applications. Lots of different things that you can do with Ruby. The origins are largely in the C community. It's kind of been driven by one guy, Matsumoto, Yukihiro Matsumoto, for years. And he's a C guy, really. And so a lot of what Ruby does depends on having access to native C libraries, running within a native environment. So start up fast, calling out to C libraries a lot, and very oriented around POSIX. So when you're doing I/O, it feels pretty much like you're calling the C functions without all the ceremony of C. Here's an example of Ruby, a little greeter class. And it looks a little strange. There's these def and end rather than braces around blocks of code. We have this at name, which is basically just a way of accessing a field in this object. You notice that things like semicolons and parentheses around method calls like capitalize are optional. There's string interpolation, where we can insert a little snippet of code into a literal string, and at runtime it will be built for us. And it really, if you compare it to the Java code, there's not a whole lot that's different. We add more keywords, we've got more syntax, we've got more typing in places. But really the code, the two examples aren't too different. And if you see these examples back and forth, it kind of shows you that Ruby is not quite so unusual. It just has a little bit different way of doing things. There it is, the Ruby code one more time. So now, why does it look like such a weird language? Well, Ruby looks foreign because it is foreign. It grew up largely independent of Java and other languages, influenced somewhat by Perl and Python, but it was developed entirely by Mots as a way to get more joy out of developing C code, essentially. Writing Ruby code rather than writing all of the C that would do these calls for him. It's also a handwritten runtime that's been developed by a number of folks over the years, and it's quite different from the JVM. There are features that it lacks, like the advanced garbage collection and JIT that the JVM has, but it also has some similarities in that it's a byte-coded runtime. It is running an interpreter, which the JVM will do for some amount of time. So there are little bits and pieces that we can bridge the gap there. So differences from Java, like all of that stuff was dynamic. That the name that I was assigning a field to, that's determined at runtime. So we have to be able to adjust objects to new fields at runtime. All method calls are going to be dynamic. Looking up constants, have to go and find that constant in a table somewhere and then cache it ideally. The standard implementation of Ruby does not have any parallel threading. They do use native threads, but they have a global lock around it, mostly because their runtime has just never been designed to support parallel threads. It's not thread safe internally. There are, however, micro threads, basically userland threads that allow you to spin up thousands of little threadlets, and that's a feature that we also have to try and support in JRuby. I mentioned that we use native libraries quite a bit. Almost every key part of Ruby is a C extension that calls out to some native C library. We also have an FFI that allows us to programmatically pull in C libraries and then call the functions as if they were in Ruby. It also has an extremely fast startup time. It's kind of been optimized for this for years. It was meant to do command line scripting, Unix scripting, and so of course that has to be able to start up and run very quickly. This is again a challenge for us when we come to the JVM. We've got people running at the command line, doing the command line style of development. JRuby needs to be able to start up quick. Now these challenges really help the JVM grow. This is why we find this project so interesting. We've been pushing on the edges of the JVM since 2006 and helping the JVM itself grow. Working with the OpenJDK development community, putting JEPs and proposals forward ourselves, helping out on projects like InvokeDynamic when that was being developed in 2007 and 2008. We're pushing the JVM just by having Ruby on the platform. Oops. Get that out of the way. All right, so let's talk through a few of these things and how we're dealing with them. So dynamic everything, like I mentioned, all of this code really is dynamically determined at runtime. There's no compiler that goes and builds your class and checks all of your methods and types for you before you run. Everything starts out as a script. Everything has to be loaded into memory at that point. So when we open up a class, that class is now basically a blank slate. We need to add in all of these methods to it. I mentioned the fields. The name field there is determined at runtime. So more code down the line may add additional fields. There's no field declarations. All of these method calls. At runtime, we need to go and look up the method on a target object, ideally cache it, and if we can get the JVM to also inline that, then we get better performance out of it. And so, of course, with no type declarations anywhere, we have to do all of this at runtime. And that's a challenge for the JVM. We are living on what is mostly a statically typed VM, and we need to be able to tell the JVM how to do all of this stuff dynamically. So JVM is built to optimize Java code. There's mostly static typing. Methods are determined at compile time, but also look lazily bound at runtime. Constant and classes are pretty much statically determined. Dynamic languages don't fit this runtime very well. The classic JVM did not give us the tools that we needed to be able to go, for example, look up a method and plug it into the code and have it optimized as if it was a Java call. That's where InvokeDynamic comes in. So InvokeDynamic was introduced in Java 1.7 after several years of development. One of our team members actually was on the steering committee for InvokeDynamic and helped make sure that it had the expressiveness required for us to represent all of Ruby. What InvokeDynamic basically lets us do user-defined binding of methods and values. We can teach the JVM how Ruby does method lookup, how it does constant lookup, and it will turn that into optimized native code. It will inline through all of those method calls. It'll optimize those constants, just as if it was statically typed Java code. Some of you may have seen this little diagram before. So here we have our switchboard operator, which is basically what we're dealing with the JVM here. So the InvokeDynamic bytecode basically allows us to call back up to the language implementation or to the library. The library can say, here's how you go and get this method. You grab the class object, you look in a method table, here is a chunk of code, this is what we're actually going to look for and call at this point. We wrap those up with little method pointers called method handles, and send it back to the InvokeDynamic. Now InvokeDynamic can basically route directly to that piece of code from then on, as if it were doing a static call. It's really pretty magical to see it in the JVM when it picks this code up and inlines and optimizes it all together. So, InvokeDynamic in JRuby, well, of course, it's heavily used. If you actually look at the JRuby bytecode that's output, almost everything in there is InvokeDynamic. Looking up fields is going to be an InvokeDynamic because we need to dynamically allocate space for the field, find the slot in the object for it, and insert it. Looking up a method, going out to the class, grabbing a method object, plugging it back into the call site. And Indy makes high-performance JRuby apps really possible. We do have an option to run without using InvokeDynamic, just to get up and going a little bit faster. But for peak performance, we really want InvokeDynamic. It makes it optimized just like Java code. So here's some examples. This is basically showing two benchmarks. One is a little Mandelbrot generator, just a command line dumping out the shapes. And then a red-black tree. It builds up a tree, it walks the tree and searches for values, tears it down, and does that many times. And this is the amount of times that InvokeDynamic increases our performance over doing it the classic JVM way. Without InvokeDynamic, we'd be considerably slower. We get 2x performance improvement on Mandelbrot, 3.72 times better performance on red-black. So it really does work to optimize this stuff. And in many cases, such as the red-black tree, we're just working with objects, we're walking a tree, the performance is very similar to Java at that point. So now how about the evolution of this feature? Well, it's been a slow process getting this to optimize. In Java 1.7, it was bare minimum. Sometimes we could get the code to optimize. It was hard to teach the JVM what we wanted. Method handles were much too heavy and didn't inline well together. But over time, it's continued to improve. And you know, it's the old Java saying, if it's too slow, just wait or upgrade to the next version, and it'll probably be faster. We also work very closely with the JVM development teams. I sit and optimize code, I run it through our profilers, I dump out assembly, and I look at the node graphs in memory to see what is optimizing and what's not. And we can tell the JVM folks that, they feed it back into the process and help us figure out why it's not optimizing the way it should. Method handles have also evolved themselves. They do more sharing, they do better optimization internally, and they've moved into essentially a little bytecode engine of their own. When you build up a chain of method handles, it will actually turn itself into bytecode and then native compile and inline like any other method call. Here's a little bit more example over time. So here's Java 8 through 11, or 8, 11, and 17, showing the improvement in performance. We've been really thrilled about this as far as the numeric benchmarks, been much faster. So rather than just 2 times, getting up to 4 times faster than running without InvokeDynamic. And that's actually about 3.28 times the speed of JRuby's JIT that they have now. So we are seeing the JVM, the promise of the JVM JIT really working for Ruby. Not as much of an increase on the red-black tree. As I mentioned, it's mostly just walking objects in memory, building up large graphs. It tends to be a little heavier on the allocation and garbage collection side, but still seeing good improvements over time. Now, we can even get better results by plugging in some of the experimental JITs that are out there. So Mandelbrot being a numeric benchmark, in Ruby, everything is an object, so we are creating lots and lots of numeric objects, lots of float objects, because they need to be represented as an object in memory, they need to be passed around as an object. When we run on the Graal JIT, we get the benefit of a feature called escape analysis, partial escape analysis. What this does is it analyzes the code, and if it sees that an object is allocated, used, and then thrown away within the same body of code, it can eliminate the allocation and just use the contents directly. That's why we get such a huge improvement here on this numeric benchmark running with Graal. Now, it doesn't always speed things up. Running on the red-black tree, performance is a little bit slower. Running on our Rails benchmarks, the Graal JIT is a little bit slower, but the escape analysis that when we do get it to work really can help improve performance. It'd be interesting for you to try it on your own projects. It can help, and I know that the Graal team is interested in feedback on whenever it doesn't. So, summary of that. Basically, InvokeDynamic puts the power of the JVM in our hands. It allows us to sort of reprogram the way that it does method calls, reprogram the way it does lookups for fields and instance data. And it's been working out very well for us. So let's move on to the next one. This is a challenging feature for us on the JVM. Fibers. So what are fibers? Well, in the new Project Loom features that come in Java 19, they're called virtual threads. They're also called threadlets or coroutines. They're basically little user space threads that can be easily switched between, won't necessarily use a native thread, but looks like doing actual parallel programming. You can have one piece of code run for a little while, switch over to another fiber within the same thread, and run that code for a while. The big difference is here, when threads depend on the operating system to do the context switch, fibers are explicitly handed off. So I will run this little algorithm for a little while, or listen on this socket for a while, and then pass that off to another fiber immediately, rather than waiting for the operating system to reschedule it. This allows us to basically switch the call stack between multiple different lines of execution on the same native thread. And I got a diagram that kind of makes this a little bit more clear. So here we have a comparison between 2 threads. The first thread is just the traditional way of doing Java development. One thread, one stack of execution. We accept a socket, and then we're waiting for I/O. Now, this thread may get descheduled while we're waiting for I/O. Data will come in at some point. We need that thread to get scheduled back onto the processor again, and we can continue handling the request. Now we send a response, and once again, this thread is just sitting there doing nothing, waiting for a response to come back. On the other hand, if we use fibers for this, or if we use coroutines or threadlets, while we're waiting for I/O, we can immediately switch over to another socket and listen on that one for a while. We can wait for I/O there. No, now the first request is actually available. We'll go back, handle that request, send a response. We can go to our other fiber. And in the same thread, rather than sitting and wasting time waiting for I/O, we can be doing additional work. And then once the I/O is ready, we jump back into the same execution. Now, this has been a challenge for us because there is no such thing on the JVM before Java 19. So we have to simulate these micro threads with real threads. Obviously, this is very resource intensive. Allocating a native thread for every one of these fibers really limits how many we can create. We can't do thousands, tens of thousands, definitely not. And switching between these different threads requires that the operating system reschedule our thread, pass the information across, and then get that other thread executing. We can't explicitly do it. We're basically waiting and hoping that the CPU will schedule the next thread as rapidly as possible. And this is even more of a challenge for us because there's more and more interest in the Ruby community for using thousands of fibers, tens of thousands of fibers, all of them doing little bits of work, reading and writing on sockets, pulling from databases. And in order for us to be able to support these applications, we have to be able to support thousands of fibers. Definitely not going to be able to do that with native threads. So here's a little example. This is basically just doing a little loop. 100,000 times it's going to create a fiber, which will be like one of these little threadlets. And then iterate over each of them and start them up, let them continue executing, and then terminate at the end. Now, if we run this on JRuby prior to Java 19, of course, we blow out the stack really quickly. There's too many fibers. We're consuming too much of the native resources of the operating system, and the JVM will easily blow up. It just crashes. We're trying to push too many threads through a machine that just wasn't made for it. And this is where Project Loom comes in. This is a very exciting one for us. So Project Loom actually brings the concept of fibers or virtual threads to the JVM. This is user mode threading. This is, you do all of the scheduling. You hand off control to the next fiber. Threads don't have to pause. We can jump into another piece of execution while we're waiting for I/O. And it's the perfect analog for Ruby's fibers, and influenced very heavily by fibers in Ruby and similar features in other languages like Python. So this is a preview now, available in Java 19, and I figured I'd try and hook it up to JRuby and see how it goes. So after spending about 5 minutes looking at the API, I went in and modified our code that creates a thread for every fiber to simply create one of Project Loom's virtual threads, V-threads. Almost zero changes to my code. It looks like it's still creating threads under the covers, but it actually is now creating these little fiber threadlets that are provided by Loom. So we can run this with enable preview. If we see that this has been turned on, JRuby will automatically switch to using virtual threads rather than regular threads. And our benchmark actually can run. We can spin up hundreds of thousands of these things, and they all will execute, and execute very quickly. The context switching between fibers is much faster than threads, and they use far fewer resources than native threads do. So finally, we're going to be able to run those C100K examples that people are starting to do in Ruby. All right. On to the next feature. I mentioned that the Ruby world is very tied in with native code, native libraries, and we need to have the same capabilities on JRuby. So there's lots of native C code out there, lots of libraries. We need to be able to call these to take better advantage of all of the resources that are available in the world. There's also constantly a need to be able to manage memory off heap. And a lot of people do this sometimes, they do this using byte buffers. They use this by calling out to JNI and having that manage native memory for you. But these are half measures. They're not good ways to do this feature. We need a more standardized way. And Ruby apps depend on so many of these C libraries, we really have never had a choice in this. We have had to build up our own way of calling out to C code and make it possible to pull in the same libraries that Ruby users depend upon. Now, we don't want to do a JNI wrapper for every one of these libraries. That would be a waste of our time, and we'd never be able to support as many as the regular C Ruby community can. So we have to be able to do it dynamically at runtime. And that's where our Java native runtime comes in. This is a set of libraries that we've created for calling out to C code. At the base, we've got JFFI, which is the one JNI wrapper that we ship in JRuby. This is just a wrapper around the libFFI library, FFI meaning foreign function interface. It's a library for calling other C libraries. You can load them in, you can query what their functions are, and then make the calls directly. On top of this, we've built JNR FFI, which is a user-facing API for doing this function binding. And then a few utility libraries where we've pre-bound a bunch of POSIX functions, so you have access to native I/O, access to a lot of native function calls that are typical in POSIX. We have ENXIO, Extended Native Cross-Platform I/O. Not my name, but it's descriptive. It's descriptive. This is basically an NIO compatible channel that is backed by native I/O calls and native select operations. So we can do full native operations on the I/O from Java, and we can do things like selecting on standard input and output. And then we also have a Unix socket library just to bring Unix socket capabilities. Of course, this is coming along for Java, I think in one of the recent releases. But it is available now if you use our library, and you get a standard NIO socket that actually is using Unix sockets under the covers. Diagram showing a little bit about how this works. We have our user code at the top, which is JRuby or Ruby code or your Java code. Calls down through our JFFI stub and JNI implementation. That goes out to libffi, grabs the function from a C library, and makes it available for call. Now, there's problems with this. Because we're calling out to JNI, we have all of the overhead of crossing that VM boundary all the time. Every time we make a call out to C, the JVM has to make sure the GC is ready for that, make sure that we're managing locks and threads properly. So there's overhead there that's not necessary for some of these calls. And also, dealing with native memory is a pain. Trying to go out to C code every time we want to access native memory, again, much slower. We're doing things that we're forcing the JVM to manage itself, manage this memory, when it's really meant to have it on the heap. It wants to be garbage collected. The other problem with this is that the JVM JIT can't see any of this. So we're doing our call down through JNI, and that's fairly opaque. Ideally, what we want is that the JVM can see that we're calling a particular C function, make that call as fast as possible, and pass those values directly through, rather than having to bounce through all of those layers of JNI code. So if I run a little benchmark of just calling out to getpid, a very trivial C function, here is some of the assembly code that will come out of that. Down at the bottom here, we can see we're basically doing an interface invoke. This is the getpid interface that we've created using JNR FFI. We tell it to bind that to the C code, but this is about as far as the JVM will get in optimizing it. It's doing our interface call. It can't see that we're actually doing a native call to getpid under the covers, and so we don't get the optimizations that we'd like. That's where Project Panama comes in. This is another feature that's come along with Java 19, experimental feature. It's a foreign function API that's built into the JVM, and the JVM JIT also can understand it and optimize these calls. So it solves that whole problem of wrapping everything with JNI and crossing that boundary. It also has a foreign memory API that allows you to manage off-heap memory, and the JVM will know about it. The JVM will be able to optimize those calls and understand how you're making those accesses to native memory. Even better, it comes with a little tool called JExtract that you can point at a C header file, and it will generate the Project Panama Java interfaces for you to make all those calls into C and have them optimized by the JVM. So let's take a look at a little example here. So here is where we had our call to the getpid interface. Now what we're looking for with JIT help is something more like this. We would like to see that our native code that's JITted by the JVM actually can make that getpid call directly. We can get that address right back out, or we can get the value of the PID back out much more quickly. We don't need to do all of that extra JNI overhead for such a simple call. The JVM can now actually make these calls directly for us. I mentioned the JExtract code generator, and this is really cool. This is one that we're looking for, we're excited to start playing with more. Here's the little example that comes from the JExtract repository. We have a little point definition, a struct with two doubles, x and y, and then a function that takes in that point and gives us a distance. So we do JExtract. We point it at that header file and give it a package we want to generate into. So in this case, we're just generating into the org JExtract. We can just generate bytecode directly, or we can have it spit out source code that we can compile into our project. And here is the code that we end up getting out of it. Some of the names are a little arcane. It has to be able to map all possible C names into some sort of Java equivalent. So there are some weird nomenclature here. Again, experimental API that this is still being developed. But this is all we need now. We run on JDK 19. We use this source file that we've generated, and we can actually make a native call to the native getpid function and have the JVM optimize all the way to that call. All right. As I mentioned, it's a preview in JDK 19, but these are still developing as we're going forward. So let's talk a little bit about one of our largest challenges. This will be the last thing that we cover today, startup time. So I mentioned that the Ruby community really just lives at the command line. They start up a new Ruby runtime for every command. They do most of their development at a terminal, a console, using an editor and a command line. That's the way they do it. JVM is just not designed to start up quickly, to do command line scripting like that. The core of the JDK starts out interpreted. All of that code has to be interpreted for a while and then optimized, and then finally it will run fast. And then we make it even worse by interpreting Ruby code in our own interpreter, and then eventually turning that Ruby code into JVM bytecode, which gets interpreted. It's a very complicated path, a pipeline of optimizations that make us run fast eventually, but damage our startup time quite a bit. So this is a diagram of the JRuby architecture internally. We take our Ruby code in at the left, and we parse that and turn it into our internal Ruby instructions. Now, we could go straight to JVM bytecode with this, but the vast majority of Ruby code, Ruby functions that happen at startup are only called once. It makes more sense for us to interpret those at the beginning, like the JVM does, and then later on optimize to JVM bytecode. So we take our instructions, we pass it into the JRuby interpreter and run that for a while, then eventually turn that into JVM bytecode and let the JVM chew on that and finally produce native code at the end. Now, clearly, this is not the best way for us to get the fastest startup time, but it does get us good peak performance. Now, one of the tricks that we've been using over the years is just to start up less, to do less in JRuby when we boot up. And that's why we added a dev mode flag. This is sort of like running with the client mode in the old JVMs. It disables our own JIT compiler. It forces the JVM to only use its simplest JIT mode, the C1 client compiler. And it chooses a simpler GC that will get up and going faster. Maybe not what you want to run in production, but quicker to boot up. And depending on what you're running, this can be as much as 2 times faster than running with standard JVM options and allowing the JVM to use the best GC and the best garbage collector, or the best GC and the best JITs. It's still considerably slower, much slower than CRuby, but it's an improvement at least. So what we have with dev mode, rather than doing the full optimization pipeline we see here, we basically cut it back down to just our interpreter and let the JVM optimize our interpreter as much as possible. Take out all of those other pieces of that pipeline, and your Ruby applications can start up at least about 2 times faster. Now, of course, this is a little hacky. We end up with people accidentally sending us benchmarks, forgetting that they had dev mode on. We don't recommend using this in production because you're not going to get the best performance, but then people don't really see what the performance is looking like on their local machines. And delaying initialization eventually still hurts us. We still have to start up these libraries. We still need to be able to optimize. So it's only, again, kind of a half measure. So what about ahead of time compilation? Of course, we've got things like Graal VM's native image, which has been very popular for small, fast applications. And we are playing with that. We've had a prototype of JRuby that can compile down to native code in a native image. But the problem is that this completely disables all the dynamic features of the JVM. We can't load new libraries dynamically at runtime. We can't use InvokeDynamic at all, really. So we have to use the slower methods of doing method calls and constant lookup. It really breaks the promise of JRuby as a high-performance runtime. Maybe that's acceptable as a local development option. Maybe you run with JRuby in a native compile, and you don't get the peak performance. You don't get the dynamic features as much, but you get fast startup. However, we want something that's going to be both fast startup and high performance. And that's where we're hoping that Project Leyden will step in the future. So Project Leyden is going to be standardized ahead of time compilation for the hotspot JVM that can start out native, boot up really fast, but then also support all those dynamic features and continue to optimize once it's been booted. There are other features coming along that we're also interested in. What if we could pre-boot JRuby and snapshot that, so we can jump right into an optimized executing JVM already? There's been some work on this in the past, first using the Linux feature called checkpoint and restore in user space. Basically, take a checkpoint, take an image of a running process and freeze it, and then whenever you need a new version of that process, you thaw it quickly, you fix up some pointers perhaps, fix up some I/O, and then start executing immediately. Now, this is a good test for this future. It's a good way to try out this idea, but it is Linux specific, and it is kind of a clunky way to do it. We've got a lot of I/O channels that need to be rewritten. We've got pointers in memory. We may have booted up resources from the operating system. Hard to fix that all up again. So the folks at one of the folks at the OpenJDK teams have decided that we need a more standard way to do this, and that's where we have crack, which is checkpoint and restore, something along those lines. I can't remember what the acronym is. Somebody had fun with this one though. So checkpoint and restore at the OpenJDK level. This is coming along very early days now, but there are prototypes of this out there that will allow you to save off a running JVM and pre-boot into it much more quickly. All right. So those are the features I wanted to cover. Now, what does this all mean for you as JVM developers, as Java developers? Well, for Java developers, I really believe that Java needs to continue to evolve. Maybe not as evolving as fast as it has been lately, but all of these new features that are coming along make the platform richer. They make it better for all of us. They make new language features possible, so we can bring things like Ruby's fibers to the JVM. We need to be able to keep moving the platform forward so that new ways of doing development and new languages can live on the JVM as well. So you end up benefiting because Java benefits as well. InvokeDynamic as a feature was initially imagined as just for dynamic languages. However, it's now being used to optimize string concatenation, to optimize lambdas. All lambdas are booted up using InvokeDynamic so that they can optimize quickly just like they would for JRuby and our blocks and closures. And this helps the Java ecosystem grow. We're not limited to just the Java language. We're not limited to the standard traditional ways of doing development. We can do things like microthreads and spin up 100,000 fibers. We can do native function operations. We can use native memory directly. The platform has grown so much wider because these features have been brought to the platform. That's all I have today. There are a few links here to some of these projects. I encourage you to check out our JNR as well for doing native calls right now. But please try out Project Loom, and if you're interested in doing some work with Ruby or JRuby, come talk to me about that too. And I think we have time for some questions. All right. Ah, yes, right here. No. So that's interesting. He's mentioning that there was the Azul had a similar feature. Ready Now, I believe it was called, that was basically allowed you to save off a pre-optimized, pre-booted JVM, or at least the optimized part of the code, and then boot back into it very quickly. We did do a little playing with that. That feature, as I understand it, was focused more on reducing warm-up time for applications rather than starting up. So the benefits at a command line to JRuby were not as much. It did mean that we could get a Rails application running full speed much more quickly, but it wasn't targeted specifically at startup time. Other questions? Yes, down here. Right. What's the benefit of using fibers instead of just traditional non-blocking? Well, you can do a traditional non-blocking pipeline where you select on multiple IOs, you find one that's available, and you continue working that way. The main benefit of being able to use fibers is that you can actually block somewhere deep in a call stack and then decide, okay, I'm not going to be able to proceed from this point. I can jump to a different call stack altogether, and that one has data available. Now I'm not using necessarily 2 threads to handle 2 fibers, or I'm not using 2 threads to handle 2 sockets. I'm using a single thread with 2 little threadlets inside of it. And that can scale to dozens or hundreds of sockets, all being handled by 1 thread. If you only did that with the non-blocking APIs, then you still would need to spin up a fiber to handle each of those sockets as they come in. Or you would need to work in smaller pieces, not down a deep call stack somewhere. Does that make sense? Okay. It's kind of hard to envision, but basically being able to switch between what look like threads and have their own call stacks and their own state on the stack without actually spinning up another fiber every time. All right, anything else? All right, thank you.